Welcome back. So, we will now state the definition of surface analytically. Since expressions are little longer, I would like to show you some PDF file. So, here more details are given. Okay. So, this is what. So, this is more like geometric definition. So, if these vectors form n minus 1 vectors are linearly independent, then we say that S is a hypersurface or simply a surface. Okay. And using linear algebra, we can convert this statement into an analytic statement, and for that you form this Jacobian matrix. Okay. You take all these gradient vectors of each function h 1, h 2, h n. There are, so they are the defining function of the surface. You take that and you write them as rows. Okay. So, there are n rows and there are n minus 1 columns, because there are only n minus 1 derivatives. Okay. There are only n minus 1 derivatives, S 1, S 2, S n minus 1. So, you form this matrix which is n by n minus 1, and from linear algebra we see that. So, the rank cannot be, because it is a rectangular matrix, rank is at most n minus 1, and it qualifies to be n minus 1, rank is n minus 1 if all there are n minus 1 rows linearly independent or n minus 1 columns linearly independent, and that we connect to the determinant, and those are called minors. Okay. So, you take all the minors of this n by n minus 1 matrix of order n minus 1. Okay. So, there are n such matrices, and you take the determinant of all those matrices, and the rank condition is that these, I call the minors as j 1, j 2, j n. There are n minors of order n minus 1. The rank condition say that at least one of them should be non-zero, at least one of them. Okay. So, that is the analytic statement of the this object S being a surface. Okay. And you can also check that, again this is linear algebra. If you take this vector, now this vector is in R n. Okay. All these gradient vectors are in R n, gradient vectors are in R n minus 1. So, this is in R n. Okay. R n, and this is orthogonal to all the vectors in 1.2, all these vectors, and thus it is. So, since they span the tangent space, okay, so this vector j 1, j 2, j n is in the direction of the normal to that surface at that point. Okay. So, everything is local. Okay. And for example, you take the case of n equal to 3, okay, and work out, and this j 1, j 2, j 3 you get can be expressed as the usual cross product of vectors in R 3. Okay. So, that is the determinants precisely come to be cross products. So, once that is done, now here is the statement. Okay, maybe just I will So, statement of the Cauchy problem. So, let me just state it for the general case, and then we come to the individual cases of linear equation and Cauchy linear equation, and then fully nonlinear equation. So, this is our first order equation, and so this is in omega in Rn, and we are given u equal to g on S. This is in omega, a surface. Okay. So, again let me repeat that surface for us is that hypersurface, n minus 1 dimensional surface. Okay. So, this is omega again, and this is S. Okay. The problem is to find a C1 solution u, because we require the first derivative only. Solution u satisfying u equal to g on S. And where do you find this solution? In a neighborhood we are satisfied even if we could find a small neighborhood of S in omega. We will see even this restriction is essential even for the linear case. Okay. So, here let me use the different S is here. So, this that neighborhood, that is sufficient for us. So, even for the linear case we will not be able to find, for example, if omega is R n, we may not be able to find a solution in the entire region R n. Okay. So, there are some restrictions, and this is the most general statement, and obviously we need to have some restriction on S. So, in this setup any arbitrary surface will not be able to do find a solution of this Cauchy problem. Okay. So, once you understand this problem, then let us see how to go about it. Okay. So, let us start with the linear case. Linear case. So, linear. So, f of that is very special here. So, let me just simply consider this a1 x du by dx1 a n x du by dxn. You can take the lower order terms also, let me write that, and even some inhomogeneous term. Okay. So, this is conveniently written as a dot product, scalar product A dot grad. So, A is the vector field. So, for each x in omega you get a vector in Rn, and that is how you get field of vectors. So, this x is in omega. Okay. So, the Cauchy problem again, let me just write it, u equal to g on S. So, S is a surface. Okay. So, this as we did it in two variable case. So, we approach the problem with method of characteristics. So, the characteristics in the simplest case, just compare this with two variable case. So, here there are so T the parameter on the characteristics A I x. One less than or equal to I less than or equal to n. Of course, we have to prescribe some initial conditions. So, let me call it characteristic C characteristic. So, this is it describes geometrically a curve in omega. If I start the initial point in omega, so this will form a curve in omega. Okay. Along C, so if that means you restrict u to C. Actually, I should define another function, but by abuse of notation we just write u t. So, this actually means u of x t. U is not a function of the t, but it is a function of x. So, this abuse of notation, and then if you use the given linear equation, what you see is by chain rule du by dt plus a 0. Again let me write x t, because we are restricting the all functions to C only. So, they are just functions of u equal to f of x t. So, this is what I was stressing. So, the study of this first order PDE reduces to the study of a first order system of ODE. Okay. Remember, just these are ODEs. Okay. And once we are able to solve this, the problem is again as you observed in two variable case. The problem is, so given a point x, x1, x2, xn, if we are able to draw a characteristics, okay, and that is where the initial surface and initial conditions come into picture. And so, this is say that yes, and this is characteristic, if you are able to do that. and we pick the data from here, and we already solved the differential equation, this one, and you pick up the data from the initial surface, and that is how we will be able to obtain a solution of the given PDE. Okay. And that is what you have learnt in two variable case, and this is where the relation between this characteristic and this initial surface comes into picture. The S has to be non-characteristic. Let me just briefly mention what that non-characteristic is. So, it in two variable case it is same as transversal to the given PD. So, non-characteristic with respect to given PD. Okay. Let me just quickly explain what that non-characteristic means and why the non-characteristic Cauchy problems are somewhat easier and characteristic Cauchy problems in general demand more conditions on the initial data, as we see an example even in just 2 dimensions. So, what is this non-characteristic? Again, let me just start with the linear case. So, this will come one by one. So, again let S be described by the function h1, h2, hn, we saw that. Okay. Just remember that. So, this parametric representation of the surface, and now we introduce what is called a characteristic set of the given PDE or characteristic variety, characteristic set or variety. So, this can be done even for more general equations and even higher order equations. So, let me just denote it by char, and it changes from S to S. Okay. So, this is let me call it L in this case, just AX dot nu x. Okay, so sorry, just confusing. Dot okay, let me write set of all j in Rn and you omit 0 because 0 is always in the set, such that Ax dot j is equal to 0. So, remember A comes from the PDE, those coefficients A1, A2, An, and if you take the union of this char x L, so L is the operator A dot del, first order linear operator. Okay. So, you take only the terms involving derivatives, and this is just formally replacing this grad operator by the vector j. Okay. So, here is the definition: a point x bar in S is called a characteristic point of course with respect to PD, with respect to L, okay, that L has to be there if nu x bar belongs to char x bar of L, that is A x bar dot nu x bar is 0. So, what is nu x bar? So, this is normal to S at x bar. So, here is S, here is x bar, and this is nu x bar. What it says is, you call that point x bar a characteristic point if the normal at that point is orthogonal to the given vector A. So, this comes from the PD, right, this comes from the PD, and this relation say that nu is perpendicular to A x bar A at that point. Okay. So, S is called a characteristic surface if all the points are characteristic points. On S are characteristic points. So, S is called a non-characteristic surface if all its points are non-characteristic points. That means, nowhere on S the unit the normal at that point nowhere is perpendicular to A. So, it always makes an acute angle with the vector A, characteristic points. Analytically, this condition is required, as you again recall the two variable case. We want to apply the inverse function theorem in order to do this thing. What thing? Just let me So, given a point in omega, we would like to draw a characteristic meeting the initial surface at some point. In order to do this thing, so we want to find the characteristic variable t and the variable that describes S, namely S. Then, because what we have obtained is here this xi and u are obtained as functions of S and t. See, here we are not yet given the initial conditions. So, these initial conditions will be on the given surface, functions of S and t. So, S is the variable describing the surface, initial surface, and t is the parameter that describes the characteristics. Okay. So, we want to obtain S and t in terms of xi, x1, x2, and for that you require implicit function theorem, and this non characteristic condition is precisely that. Let me just mention that. The non characteristic condition is essential for the use of implicit function. For applying implicit function, and in two variable case it was called transversal condition. Okay. So, that is the only terminology is different, but this one is applicable in the general setup and also for higher order equations. Okay. So, this terminology is more used in the context of PDs. So, what about the characteristic Cauchy problem? So, let me just give an example, very simple one, which you already seen it in some way, characteristic Cauchy problem, and what are the difficulties. So, consider the very simple first order equation. So, A is a constant. Okay. So, if we are given at t equal to 0 is a non characteristic here in this case, because we know what the characteristics are u0 x. I am considering this in x in R, t positive. So, this is simple transport equation, and the solution is u0 u of x t So, here u0 is any C1 function, arbitrary C1 function, and we are able to solve this equation explicitly in this case and uniquely. Okay. So, what are the characteristics here? The characteristics are simply given by dx by dt equal to a. So, they are straight lines. So, x is equal to x0 plus at. Okay, so, let me just draw that. Suppose a is positive. So, these are the straight lines with slope. So, this is x axis and this is t axis. Okay. Now, suppose we give the initial condition on one of these characteristics, and that is called characteristic Cauchy problem. So, you take any characteristic of the given equation and you prescribe the initial condition on that. So, suppose I prescribe initial, instead of the line t equal to 0, this is line t equal to 0, initial condition on one characteristic, any characteristic you take. Say this one is passing through some x naught here. So, I prescribe the initial condition on this. What happens? U equal to u0. So, can u0 be arbitrary? Can u0 be arbitrary? So, in this case, first of all, the differential equations tell that u is constant along the characteristics. Okay. So, I cannot arbitrarily prescribe u0. u0 has to be a constant along this. Okay. u0 is a constant. And then what about at other points? The other points do not intersect this characteristic anywhere. So, it is totally arbitrary. I can prescribe any value at any other point. So, there is, first of all, u0 has to be constant. So, restriction. And if you want this u to be a C1 function, that u has to be constant throughout. I cannot take another constant and demand that it is continuous and differentiable. Okay. So, if you prescribe the initial condition on a characteristic, we face problems, and there is only one solution, namely u is equal to constant, nothing else. Okay. And in higher order equations, such problems arise if you want to prescribe the Cauchy problem on a characteristic. Okay. That is why we avoid Cauchy problems on a characteristic, and we will just consider non-characteristic Cauchy problem. Okay. So, let us go back to linear case and one simple example. Okay. So, example again. So, let me take the constants as coefficients instead of action. Maybe I will just add one more variable just for simplicity, otherwise I have to divide by. So, I am actually considering, so x is in Rn and t I can just take positive. So, this is transport equation in more than one dimension. Okay. So, this is, so i's are constants, for simplicity I am taking. And let me use the variable t itself for the characteristics. So, I prescribe, okay, let me come to that. So, dx I by dt is equal to a I. Okay. And t variable is there. So, dt by dt equal to 1. So, that is and you easily check that t equal to 0. So, these are again straight lines even in n dimension. So, it is difficult to draw the picture here. So, the solutions immediately we see that x I t is equal to a I t plus x I 0. So, where x I 0 are the initial conditions for this n equations. So, if you take constant, it is very easy to integrate this differential equation, and you call this as again a characteristic. So, along C again by abuse of notation. So, if you write this u of t, now it is u of x t t, because I am using t itself as a characteristic parameter, and this you immediately see that du by dt again by implicit differentiation, you see this is du by dt plus summation a I du by dxi, and that is 0. So, that means u is identically constant. So, that means what? U of t is equal to u of 0, that means u of x 0 0. And so, if I give the initial condition, this is u 0 of x. So, u 0 is a given function and t equal to 0 is a non characteristic, and if you use that initial condition, and these are the initial condition at x I 0, these are all x I 0. So, if I express that one, so you just get u 0 x minus 80. So, exactly similar to the one dimensional case, that means n equal to 1, but only thing is now you see that this is in R n, okay, x is in R n. Okay. So, that what this equation describes is just transportation. So, initial whatever initial profile is transported in time in different directions. So, this if you expand this whole thing, okay, there are n components x 1 minus a 1 t comma x n minus a n t. Okay. So, the initial profile that u 0 is transported in time in different directions. So, it is with there are speeds, different speeds, they are given by this coefficients a 1, a 2, a n. So, similarly in general linear case you can just follow this procedure, and the non characteristic condition helps us to use the implicit function theorem, and in principle we can solve the first order linear equation without any problem, provided we prescribe the initial condition on a non characteristic surface. So, for example, here what is the surface? Surface is just t equal to 0, that is n dimensional space R n. So, here we are in n plus 1 dimensions. So, we are prescribing the initial condition on an n dimensional, in fact, here it is a subspace, it is a subspace. So, this is also an example of a hypersurface. So, with that we come to an end of this discussion on linear equations, and in the next class we take up the study of Cauchy linear problems, and then briefly the fully nonlinear equations. Thank you.